Okay, so I want to start encoding some more instructions, starting with arithmetic ones, so add, sub, MUL div. So we'll go to the test data and create arithmetic dot asm 64-bit. We'll start with add, so we'll do add, and I've got the encoding table open here, and I basically want to hit each form, if possible, with some tests. So in the case of add, we've got these special accumulator cases where they can be encoded using a single opcode byte instead of an opcode byte with a mod rm. This doesn't include AH, so AH will actually be in this form down here for the immediate source. And in the cases where we've got immediate bytes going into higher width registers or memory locations, we have these special cases here where the immediate is sign extended into the larger width. Then after those, we just have the normal cases of RM and register being on each side. But the other thing to note about this is that up until now I've been working on things like MOV, and MOV allows, for example, in the 64-bit register case, it would allow, for example, a 64-bit immediate, but that's unique to MOV, and the rest of them, when you're doing an immediate form or an immediate instruction, they go up to 32 bits in length. So we'll start by creating some tests for these accumulator special cases. So we've got AL, which is bytes. Then we've got AX, EAX, and RAX. So we'll do 16 bits for this, 32 bits for this, and then this one should also be 32 bits actually, so that's fine. Then we've got register or memory with each size. So we've got bytes 16, 32, and 32 again, but up to a 64-bit register or memory location. So we'll do the registers first. And to make sure that I'm not testing the special case for the accumulator here, I'll just use the C register instead. So that is the registers, and we'll include CH in this one as well. Then we just need the same thing, but with, let's say, RCX as a memory operand. So we'll get rid of one of these, and this will be bytes, word, dword, and qword. So that should cover these ones, but I need to do... so that should cover all of these ones, I think. Then we've got these special cases of 8-bit immediates going into word or higher. So this will be register or memory. So we'll keep these ones, we'll just cut them down to being bytes. And then we'll also do the same with registers as well. So this one would be CX, this would be ECX, and these just have bytes going into them. Then we've just got the normal cases of register memory register or register register memory. So in this case, we'll just do, let's say, why don't we do some different things here? So maybe we'll do, instead of C, we'll keep C actually. We've got 8, 16, 32, and 64. So we'll include CH here again. But this side, instead of being an immediate, now it's just going to be a register. So in this case, we'll do like an extended one maybe. So this will be B, B, W, and D, and this one is unaffected because this is already 64 bits. Then we've got the memory cases. So maybe for this we'll just do memory for RCX with these registers on the side. Don't need this one anymore. And we'll copy these bottom ones to flip around the memory operand. So I think that should be enough. We'll just do NASM codegen x86 test data arithmetic. Generate a listing for that. Test data arithmetic.lst. Cannot use high byte register. Oh, yeah, okay, that's because I can't use an extended register with a high byte. So in this case, we'll use, let's say, DL or something instead, or DH, let's say. Okay, so that's the listing generated. So now I just need to go and add these to the encoder tests. So we'll create a new one here called arithmetic. Okay. So these need to be op-add. Then we're going to have some size. Then we'll have, let's just do CX here as the placeholder. Then some other operand, and then we've got NA for all of them. So in these cases where it's an OX7, these are all immediates. So we'll just go across to the second operand here and just do immediate with that value. Then we've got, for these top ones, these are AX special cases. This one down here with CH should be CH over here. There's another CH and DH down here, so let's just do those now. We'll do CH and DH. Then we've got, okay, so let's just fill in the rest of these operands down here. So here we've got R9 for the rest of these operands. So this is R9. These ones are also R9. And then these ones are R9, but they are switched around. Then we've got some memory accesses. So we've got square braces or square brackets over here. So this will be C.M. Here we've got memory access as well, and then these final CX ones here are also memory accesses. Okay, so now just the sizes. So we've got bytes, word, dword, and qword. These are the same down here, but we've also got bytes at the top there. Then we've got the same thing here. This one is just word, dword, and qword. Same goes for those ones actually as well. This one is byte, word, dword, qword with an extra byte one on the top. Then we've just got the same for down here. And then these ones are the same as word, dword, qword. Okay, I think that should be fine. So let's just get rid of these comments. So now if I'll need to add add, so let's just add that under or above mov here. So we've got op-add. And then if I run this, now we don't match any forms, so that's fine. So we'll go to forms, and we'll add one for op-add. So we'll do that here, op-add. Okay, so matching each of these forms. So first starting with this AL or accumulator special case, there's actually another operand encoding here that I don't have yet, which is I. So I being that the only thing that you need to encode is actually the opcode and the immediate. You don't need to encode any of the registers or anything, because the register, the accumulator register, or AX, is basically just sort of hardwired to be these opcodes. So we've got opni, which means that this is going to have no mod rm. So we'll put this in here, opni. And then we just need to add some forms for this. So we've got width is byte. The opn for this one is opni. The register, or the op1, is expected to be the AX register. So we'll need a new flag for the operand to tell that it is the A register. So we'll call that RA. And in AX here, we'll just add another flag. So let's just add that to the flag list. Okay. So if we've got the A register with an immediate as op2, then this is opcode 04. Then we need one for word, dword, and qword. And these ones are 5. Then what we need is register or memory with an immediate. And again, we've got 2 different opcodes for byte and the rest of the sizes. And these are op and mi, mi there. So op1 here is going to be register or memory, op2 is an immediate, and these ones get the opcodes 80 and 81. Then we've got some special cases here for only word, dword, and qword. These ones are still operand encoding mi, but they specifically need the second operand to be an immediate 8 bits. So I'll put that one above this one, because these two are going to score the same based on the flags in their operands. So in the case where the widths overlap, in that case, the winner in a tie-break situation is just whichever one came first. So we'll put this one above this one, because the 8-bit immediate optimization is the one that we want to do in preference to this just normal one. So then we've got the register, the RM and register cases. So if we just take this and copy it down, so these ones are so we'll start with MR, because RM is M, and then register is R for the operand encoding. Then this one is going to be regmem, and then instead of immediate here, this one is going to be register. And this one down here needs to be register as well. So these ones get an opcode of 0 and 1. So 0 and 1. And then we've got the opposite case where we do opn rm. So in this case, we'll just move the mem flag to op2. And these ones go 2 and 3 down here. Okay, so let's run those tests. Unsupported opn, yeah, so I need to go and add a case for this. So this is opni, which is that we don't really want to do anything with the operands, so we'll just add it to this case here. Okay, so now we are actually passing quite a few of the test cases already. It seems like so in this case, we're getting an incorrect mod rm. And then down here somewhere, we've got this one is outputting a 16-bit immediate when it should be outputting an 8-bit one. So maybe we'll fix the immediate thing first. So we'll go down to the bottom to the immediates, and so I'm looping over all the operands and only outputting an immediate if it is actually an immediate. And actually, I've just noticed I'm outputting op2.value even though I'm looping over these with O now, so this should be O. So what I'll do is say that, for example, in the optimization case, I'm saying that it's specifically going to be an immediate 8, and I'm not including this general immediate flag here. So I think what I'll do is just say that the immediate width will just assume to be the width that was passed into the emit function. But if the form operand flags that match the current operand that we're on don't have that immediate flag, the general one, then we'll assume that it has a specific size one and we'll change to outputting that size if it exists. So I'll actually need the forms as well. So this will be the f-infos. This will be an array of 4 uint64s. So this will be the form that I matched, op1, 2, 3, 4. So we've got 3 here and 2. Then we need to find the correct form info. So this will be sub I for whatever operand we're on. So then we'll say that if the form info, if it doesn't have the immediate, it'd be nice to have the is thing here. So we'll say if it's not an immediate. So I think I'll need to go and change these uint64s. We'll call it like flags or something. So this is flags. We'll go to the forms. This one we'll call flags, which means that this can be flags as well. And that also means that actually the operand can take flags as this here. So we'll just create flags here. This will be uint64. And we'll have the function f flags is, I suppose we'll have is and is any. So these can just pass through to the flags, I suppose. So this will be, for example, info.is with the mask. And this can be is any with the mask. So I'll just copy these helpers up here. Change it to flags, and then instead of o-info, this will just be f. And that also means that masks here can be flags. We've got overlap as well. This is going to be flags now, so we'll change it to uint64. Okay, let's just run that and see what compiler errors we've got. So cannot use info. Right, yeah, this should also be flags. And I suppose that actually now I can actually give this a type of flags as well. So then we're not using immediate width. So we'll switch on immediate width instead. Okay, so now we can just switch on whichever one it is. So we can say fi is immediate 8, then width is a byte. If it's 16, then it's going to be, well, not width, we're going to change immediate width to word. In the case that it's explicitly a 32, then it's a D word. And then in the 64-bit case, it's a Q word. And I will have a default in here to catch any you know, cases where we don't have a specific size to panic. So we'll say could not determine immediate width. Could not determine immediate width. So if this if this is not immediate in the form info, op 1, 2, 3, 4. Then we try to do this. Let me just take this out and see what we get. Oh, so it is actually doing this. Oh, yes, I suppose in this case, all right, we'll leave this out. Okay. Okay, let's go back to the forms again. Okay, let's just rerun the test. So now I'm getting an incorrect mod RM for CL. So I wonder if I've done my tests correctly, first of all. So we've got AX here, we've got CL. Yeah, so not all of them are incorrect. So we've got 80 C1, 80, but we're outputting 80 F9. Let's just go and have a look at the mod RM table. So if it's C9 that we want to have, or C1 that we want to have, so we've got C1 would be down here. That's where RM. Okay, have I done the correct operand encoding for these? So we've got 80 here. This is MI encoding. Let's go back to add. This one is MI, so that's fine. Oh, opcode extension, that's why. So these ones have an opcode extension of 0. And these special cases do as well. Okay, so that's why it's outputting the wrong thing. So these ones here need an opcode extension of 0. Okay, so now I'm just selecting the wrong encoding for these. So this should be 8.3 for the sort of optimization case. And then finally we've got CH. In this case, we got C1, but we want C5. We're getting the correct opcode, so that's fine. Have I just, I think I just need to change this to CH here. Okay, so that's adds done. If we move on to sub, so let's see, where is sub? Sub is here. Okay, so sub is basically the same as add. You can see it's got all of the same special cases here and here. The difference is that there's a different opcode extension and different opcodes themselves. So if we go to the arithmetic assembly, I can just copy add here and do sub instead. And let's just regenerate that listing. We'll go to the encoder tests, take all of these add ones, and do sub. So this will be op sub. Now if I do a test, these should all fail. Oh, op add, I need to add sub here. And then I also need to add the forms actually as well. So if I just copy add, Okay, that's fine. And then instead of opcode extension 0, these are 5. And then I just need the correct opcodes. So the AX ones are 2C and 2D. So 2C and 2D. Then we've got 80 and 81 still, because these ones are opcode extension cases, so that's fine. And then in these cases, it goes to 28, 29, 28, 29. And then these just count up again, so this is 2A and 2B. Okay, so that's sub done. Now if we do, I think I want to do maybe IMUL first. Or actually, let's go look at MUL first. I think MUL is a simpler case. Yeah, so MUL is just the opcode extension with a single opcode. There are barely any tests here. So this is literally register or memory. So we'll go back to the arithmetic tests. So we'll basically just take these and call these MUL. So let's just say bytes, word, D word, and Q word. And then we've got each size here as well. So yeah, it's just 8, 16, 32, and 64. I won't bother testing like different extensions and things like that, because that's already tested in plenty of other places. So let's just do NASM again. We'll take these across to the tests. So these are opmul. I'll just put byte in here. We'll do R9. There's nothing here, nothing here, nothing here. And then we've just got the sizes. So sizes are word, D word, and Q word. That's going to be the same down here. And then all of these ones here are CX with memory access. So if we, I'll need to go to the op sub. Let's just fill in a few of these. Actually, we'll do mul, we'll do div, we'll do imul, and we'll do IDIV. I think that's okay for capitalization. Maybe I'll just do single, like this. Okay, so I've got all those. We'll go to forms, create one for MUL. So this only has 4 cases in it, so that's fine. We'll do div here as well. Let's just empty that out. Then we've got IMUL and IDIV. Okay, so in the byte case, this is F6, with the encoding is just M here. So we'll do M, which means we're going to need to add another op N up here. And in the case of just being a byte, this will just be register or memory. We don't need op2 here at all. And then the opcode itself is F6. Then we've got F7. Don't need the opcode, the op2 for this. We'll just do reg memory again. And then, yeah, we'll just see how that goes. So go tests. Okay, so unsupported op n in the encoder. So this is mi, which means that it's just going to be the same as this one. So we'll do op n m. Okay, so we've got the incorrect encoding for the mod here. Okay, let's see. So we've got rm is op1. Yep, that's that should be okay there. But in the case of, oh right, so these are opcode extensions as well. Yeah, so I keep forgetting about these. So opcode extension is opcode x4 in this case. Okay, that passes. So now we can do div, which I'm pretty sure is similar to MUL. Yeah, so div is the same, but it's just opcode extension 6. So let's just go to the test cases, generate some for div. So this should fail with, let's see, fail with a panic for a mismatch. Oh, yeah, okay. So encoder tests, we just need to add some for div. Div here. Okay, so it fails on not being able to match a form, so that's fine. So if we copy the MUL ones and rerun, this should fail. And then if we change to, I think it was 6, now it passes. So now we can move on to IMUL. So let's find IMUL down here. So this is basically the same as MUL in these 4 cases, but then we have extra cases where we get 2 operands and 3 operands. So let's go back to here. We'll basically take these div ones. These can all be IMUL, because that covers these top cases here. Then in the case of having register RM, so in IMUL, when we've got more operands, the operand 1 is always a register and operand 2 is always the RM. So let's just go and create some of these. So we've got register and then potential memory. So we'll do these ones. So let's just say we're going to do CL, CX, ECX, and RCX. So that covers the register ones. Then we've got memory. So that covers these 2 operand ones, and actually the 2 operand ones don't have a byte version. Then we've got 3 operand ones, where we've got some special cases for 8-bit immediates, and then we've just got the normal cases again. So we'll just take, maybe we'll just take the, yeah, so 3 operand all have immediates on the end. So we'll just take some of the immediate tests from here, and we don't have, okay, and we don't have like a 8-bit cases, so we can just take the word ones. So let's just take these ones. So these are IMUL. This is for, I've got the memory ones right now, so these need to go into some register. Then we've got memory access. Maybe I'll do, yeah, so we've got immediate 8s. I'll just do immediate 8s first because that's just the order they are in the table. So we've got register, memory, and then we've got immediate 8. So we've got memory, immediate 8, and we've got register here. Then we'll do the same thing, but with register. So this is E, this is R. And then we've got the same thing again, but this time without them being immediate 8s. So in this case, I need this to be 16 bits. And these ones can be 32 bits. Okay, and then I just need to take these and put them down here. I think that should cover everything, so let's just see if Nazem has anything to say. So invalid combination of opcode operands 113. Yes, this can't be done, so this has to be, let's say, or maybe we'll just use, oh no, wait, that 113, invalid combination of opcode and operands. IMUL. Oh yeah, because it's we don't have the ability to do byte sizes with this. And actually, yeah, so the only one that has a byte size is this single operand case here. Okay, so that's fine. So let's go and add these to the tests again. So we'll have op IMUL, some size, then we've got some, I suppose it's mostly R9 in this case, and then some CX ones. Then we've got, I suppose I'll just fill these in separately because we've got different things. NA is always the last one though, so this one here is that they are NA and NA here. And these ones are CX memory accesses. Then we've got the same thing here, so we've got NA, NA. And here this is R9, so that's fine. Then down here we've got CX with NA, so this is the two operand cases. CX with memory. And then these ones down here are all immediate, so let's just fill out the second operand first. This is CX. This one is CX with memory access. This one is just CX, and this one is CX with memory access. So then we've got immediates to fill out. So those will go here. And then finally we've got to fill out the sizes. So we've got bytes, word, dword, and qword. Actually, these ones are the only ones worth copying here because this is the only one that's got bytes. So then let's just put these in here. We'll do it in there, and then this one. Okay, I'll leave the comments there just in case I've made any typos. Okay, so no forms matching. So the MUL and so these top ones are the same. This is just that it's F6 and F7, but with a different opcode extension. So these ones are 5. And this is regmem for operand 1. Then we've got regmem with 2 operands. And these ones don't have an opcode extension, but they do have an opcode map of 0f. So before the opcode we'll put map, this is map 0f. Then we want to match on op1 being just a register. And then op2 can be a register or memory. And the opcode for this is AF in this case, AF, and we don't actually have a byte case for these, so that's fine, we can get rid of that. Then we've got the 3 operand case, which is the same thing, but it has a third operand. So we've got op3. This is an immediate, we'll say immediate 8 for the optimization case first. So this is going to be 6B We've got 6b here, no map for this one. And then for this case, we've got just any other immediate, and in this case it's 6, 9. Okay, so let's see what's going on here. So we've got IMUL, we're getting an incorrect rex prefix. This is specifically for the 2 register one. Oh, I need to set the operand encoding properly as well. So this one is RM, and then these 2 are RMI, which I don't have yet. So we'll add another one up here. So we've got opn RMI. Let's see, we'll go back to here. So in this case, it's just going to be this one again. Okay, so that passes. So now if we just go and finally look at IDIV. IDIV is even simpler, so this is just the same as div. So let's just go to the tests. We'll take div, and then down here we'll put IDIV. So we've got 8, 16, 32, and 64, register or memory, and it's got the opn of M, so this is F6 with opcode extension 7. So I can just take the DIV test cases here, put them down here, and instead of opdiv, this is going to be opidiv. I'll just get rid of these comments as well. Then we'll just regenerate the listing, and let's take the forms for opdiv and put them into the IDIV one. So this should fail because the opcode extension is incorrect, and I'm missing encoded test 305. Here, okay. So we do a test, this fails, but if I change this to opcode extension 7, it now passes. Okay, so that's basic arithmetic instructions done.